Okay, so we're going to be looking a bit more at vectors. Specifically, we're going to be talking about the magnitude of vectors, the direction of vectors, and then finally this concept of position vectors. Magnitude and direction is one subchapter of the book, and then position vectors is another, but I've kind of combined them here into one, just because individually there's not that much substance to them, but combined there's quite a bit we have to cover. So just to start you off, I'm effectively going to be answering how to do this on the next slide, but you may know how to do it already, so give it a go. What is the length of the vector 2i plus 3j? Have a think about how you could solve it. Okay, and then assuming you paused and did try, or perhaps you did it in your head, you've got 2i, so that's 2 to the right. You've got 3j, so that's 3 going up. Okay, that's our 2i, that's our 3j. And our actual vector, I'll do in blue. Okay, that's the vector we're actually talking about. This is the 2i plus 3j vector. It's just the hypotenuse of a right-angled triangle. Right, this is definitely a right angle by definition, because I and j represent perpendicular vectors. So therefore, our final answer is the square root of 2 squared plus 3 squared by Pythagoras, which is the square root of 13. And that'll do as an answer. Okay. So let's take that concept then and just generalize it a little bit. So that's going to help us formally define magnitude. So let's say I have a vector, and let's clarify at this stage a 2D vector. So a two-dimensional vector. So in general, a 2D vector will be something I plus something j. Or alternatively, to make it easier, I'll just write it as a column vector. So it's something, let's call it xy. Right, we could also call it AB, doesn't particularly matter. So that's our 2D vector. Has a magnitude and the general case will be the square root of x squared plus y squared. Okay, that's the magnitude of the vector xy. And the reason is effectively what you just saw on the previous slide. The magnitude is the hypotenuse of a right-angled triangle. We denote, so this is notation, the magnitude of a vector let's give it a name, let's just call it A. And this is how you denote the magnitude. Okay, so this bit here, this is our vector, and then this thing here, this is the magnitude of the vector. And it doesn't matter how you represent a vector. You could use IJ notation, you could use column form, you could use the 2 points that the vector connects. Either way, it's always 2 vertical lines either side, and that denotes the magnitude. So 2 vertical lines on either side of a thing denotes the magnitude of that thing, specifically when the thing is a vector. Okay, so that's magnitude defined formally. It's effectively the length. Okay, so then I suppose let's split screen for a moment. Okay, let's do direction. So the direction of a vector, it's very similar to bearings, but with a slightly annoying difference. That difference being where the 0 is. So let me clarify slightly. If I draw, let's just do some diagrams. I'll draw some random vectors. Let's say here and okay, these 3. Okay, and I'm just going to mark on each of them the direction. So the direction is effectively the angle, right? So let's note that in brackets actually. Magnitude is effectively a length. Direction is effectively an angle. But how do we measure that angle? It's as follows. In that first case, it's that theta there. In the second case, so we've got that, and here we're going to take that as our angle, quite a large one. Okay, so to just clarify here, the first, in all cases, what we've done is we've taken the positive horizontal axis, or the x-axis, and we've gone anti-clockwise. Okay, so here we went along the right axis, horizontal axis on the right hand side, and then went this way, and that measured the angle. Likewise with this vector, that's how we measure the angle, and with this vector we started on the positive x-axis, went anti-clockwise all the way around, and we measure the angle. Okay, so you can see, for instance, that first one, it's something like about 30 degrees, that one is something a bit more than 90, and this is something a bit more than 270. I'm just going to point out now though that this is the sort of standard mathematical convention, but at least within the textbook at this stage it tends not to formally define it quite this way. It leaves it a bit ambiguous, and it says you can measure the direction either with respect to the horizontal or with respect to the vertical. It's up to you, it depends on the question. Now that's fine if a question states, you know, what is the direction with respect to the y-axis, measure the angle from there, you can still answer that question. However, I just want to make it clear that by default, if you're not told, then the convention tends to be positive x-axis and then anti-clockwise. You might think, for instance, in this case, you'd be tempted to give this angle, right? And quite often that might be what you're asked to do, but then it will be specified. It will specify measure the angle with respect to the x-axis clockwise or something like this. But by default, go anti-clockwise and start from the positive x-axis. How do we then find these angles? Well, let's take this one as a simple case and just throw in some numbers. So let's say this is the vector 3i plus 4j. Okay, so this is 3, 4. How do I find its direction? Well, add in your sort of horizontal and vertical lines so that it turns into a triangle, and then mark the angle you're actually interested in. It's this one. I want that theta. And then you can just use a bit of trigonometry. You know that that length there is 3 on the bottom. You know that this length here is 4. You've got two sides, you've got an angle, therefore you can find the hypotenuse. The hypotenuse of a right angle triangle will be arctan of opposite over adjacent, right? So in this case, the direction theta is equal to the inverse tan or arctan of opposite 4 over adjacent 3. Okay, and you put that in your calculator, you get a number, and that's your answer. You have to be careful though, because for instance, if it was that third vector, you should draw the diagram, and you're probably going to find the angle here where my laser is, and then you'll do 360 minus that to get the actual blue angle. So you can't just blindly do arctan of the second component of the vector divided by the first component. Don't just do that, because sometimes you might get the wrong angle. You'll still get a useful number, but it might be the wrong angle. So always draw the diagram, identify the actual angle you're interested in, and use trigonometry, and just use it sensibly. It's good to have a picture of the vector in front of you. Okay, so that's it. You should know how to find the magnitude of a vector, you should know how to find the direction of a vector, and you should know what each of those words actually means. Okay, and then before we try some examples, it's good to introduce now this concept of a unit vector and how you get unit vectors from other vectors. So a unit vector is really simple. All it is it's a vector, but the length is 1, right? So a unit vector, any vector with a length of 1, or in other words, magnitude 1. Okay, hence the word unit, because the word unit mathematically just means the number 1, right? So they're kind of like 1 vectors. So these unit vectors have magnitude 1. You could think of some examples. For instance, the I vector and the j vector, remember I and j, they are unit vectors because I is length 1 to the right, j is length 1 upwards. If I could give you another example, the vector which is, let's see if I do this right, hang on, the vector which is 1 over root 2, 1 over root 2, okay, that's also a unit vector. Consider why. It's going the same amount to the right as it is up. Okay, so that's 1 over root 2, that's 1 over root 2. Do a bit of Pythagoras. If you square the two known sides, you'll get a half. Add those together, you get 1. Square root, the length is 1. Okay, so that's also a unit vector. There's infinite unit vectors. You could imagine, take all the possible directions, and there's 360 degrees, but that can be further subdivided, so there's infinite directions. So you've got infinite unit vectors, effectively. But those are just some sort of classic examples. Now, there's one other thing to mention on this topic of unit vectors, which is if you have a vector of any length, you can convert it into a unit vector. And what that means is you take any vector and you just make it shorter or longer so that the length becomes 1 and the direction stays the same, right? And there's a very simple method to do this. So let's just write this down. So any vector of any length can be converted into a unit vector. And here's how you do it. Let's say we've got the vector, I'll make something up. Let's do something easy, 3, 4. Okay. So that doesn't have a length of 1. What length does it have? Do your Pythagoras, and you should be able to easily find that it has a length of 5. Okay, so the vector 3, 4 has length 5. So if something has a length of 5, if I divide every component of the vector by 5, it will become length 1, because 5 divided by 5 is 1, right? That's a little bit, that's glossing slightly over quite the reason, but that's the idea. If I shorten the 3 and the 4 by a factor of a fifth, then the hypotenuse also becomes a fifth in size, which in this case then becomes 1. So as a unit vector, this is 3/5, 4/5, and that has a length of 1. Okay, and if you're not unconvinced, you can double check it. 3/4 squared plus 4/5 squared, all square rooted, should just give you the number 1. Okay. So let's just, before we move on, let's just write this as a formula. I'm just going to clear some space. A unit vector in the direction of a vector, let's call it A, and I put the line on top to distinguish it from my use of A as an English word. So a unit vector in the direction of a vector A is A multiplied by 1 over the length of A. And that's it. That's our sort of general formula. Okay? And that's very important to remember. Let's just write it a bit more succinctly. And you've got it basically there as a nice sort of standard formula. Okay? Just keep in mind that this thing on the right, this is clearly a vector. This thing on the left, this is a scalar, this is a number. And therefore it makes sense. We can multiply vectors by scalars and we get a vector. Okay, so that's it on unit vectors. We haven't talked about why they're useful or why we're going to use them yet, but it's important to know what they are and how you can convert any vector into one. Right, so let's look at some examples. Okay, you're given two vectors, A and B. Find the magnitude of A, find a unit vector in the direction of A, find the exact value of the magnitude of 2A plus B. These are very simple, basically just arithmetic style questions, but I'll just quickly do them to make sure that you know how these would work. I always advise, if it's easy enough, try and do it yourself quickly and then just skip to me giving you the answer. If you're not sure, then just follow along. So A, I'm going to just quickly rewrite as 3, 4. The magnitude of A is, oh, that's exactly the example I gave before. So that's the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, 25. There we go, the answer is 5. Part B, find a unit vector in the direction of A. Let's just label that as part A, and then part B. So we're going to do 1 over the mod of A, or I shouldn't say mod of A, I should say magnitude of A, times the vector A. So that's 1/5 times 3, 4. I'm repeating myself a bit here, feel free to skip. And that's 3/5, 4/5. Okay, I just happen to give the same example. Okay, and then C is going to be magnitude of 2A plus B. So you first want to work out, well, what is 2A plus B? Let's do it up here. 2A plus B is equal to 2 times 3, 4, plus minus 2 minus 4. So I make it 4, 4. So then I go back to C, and this is the same as finding the magnitude of 4, 4, which is the square root of 4 squared plus 4 squared, which is root 32, which I think we can further simplify to being root 16 times root 2, which is 4 root 2. And that's it. Okay, let's look at the next example. Okay, find the angle between the vector 4i plus 5j and the positive x-axis. Okay, so this is where it gets a little bit ambiguous and slightly annoying. That's partly because at this level, sort of year 12 level, they tend to try to not give you the convention, which is the positive x-axis anti-clockwise. So for now, because they've specified, just pick the small angle between the vector and the positive x-axis and don't use the default convention because they've specified. Draw the diagram first, then you shouldn't make any mistakes. So there's a vector. That's length 4. That's length 5. This is what I want, especially because that bit there, that's the positive x-axis. And therefore we can use trigonometry quite easily. It is just inverse tan of of the opposite, which is 5, over the adjacent, which is 4. And you put that in your calculator, you should get something around approximately 51.3 degrees. And that's it, there's your answer. Okay, and then finally, if you're given a magnitude and you're given the angle, you might want to convert that into the vector, into the actual vector that you want. So you just do trigonometry again, but in reverse. Now here, as I said, notice, annoyingly, they've done exactly this thing. They've given you the angle 30 degrees, whereas I personally would say that the direction of that vector is actually 60 degrees. But it doesn't matter really, because you can either use the 30 or you can use the 60. It depends how you draw your triangle. I'm going to go with 60. So I effectively want the following vector. It has a direction of 60 degrees. It has a magnitude of 10. So you do your trigonometry. Your opposite is going to be sine of the angle times the hypotenuse, and your adjacent is going to be cos of the angle times your hypotenuse. Technically, if you're at a good level, you'd know sine 60 and cos 60 off by heart. One of them is a half, one of them is root 3 over 2. Perhaps you can remember which is which, but in this case that gives us sine 60 being root 3 over 2 times 10 is 5 root 3, and cos 60, which is a half, times 10 gives me a value here of 5, and therefore my final answer will be the x horizontal component, which is 5, and the y vertical component, which we've calculated to be 5 root 3. And that's our answer. That is A. So this particular vector here has got a magnitude of 10, and it has an angle of 30 degrees with the j. It says here with j, which effectively means the y-axis. Okay. Right, so that's the sort of first subchapter done. I do just need to talk a little bit about position vectors before I give you some questions. So let's see if we can also just cover position vectors, do a couple of examples on those, and then you've got some questions to try. So we just want to define what a position vector is and make sure we understand the difference between position vectors and just regular vectors. And there isn't really too much difference. So a position vector, simply put, is the vector you get from a coordinate on the xy axis. Okay, so if I had, say, a pair of axes, xy, and let's say this point here was 7, 2. Okay, so that's a coordinate. It's not a vector, it's a coordinate, even though it looks like two numbers, it seems like it's the same thing. The position vector is the vector which starts from the origin and ends at that point. Okay, and what is that vector? Well, it just happens to be 7, 2, right? So it seems almost a bit pointless. It's almost like we're saying, what's the difference, coordinates, vectors? But there is a subtle difference here. The idea is that a coordinate represents a point, whereas a position vector is a line. It has a magnitude and a direction, and it goes from the origin to that point. And there are many things they have in common. For instance, the two numbers, the pair of numbers they have, but they are different mathematical objects. One is coordinates, the red one is coordinates, and the green one is a vector. Okay, and other than that, position vectors don't differ from vectors. They are just vectors, but they have this property that they were usually derived from a coordinate. Okay, hopefully that makes sense. So they have all the same properties. So this green vector I've drawn is just a vector, but we call it a position vector because it represents a coordinate. So what that then means is if you're given a point A, you can get its position vector. So let's just define that formally. Okay. And before we do that, we should define formally the origin. By default, always we use the capital letter O. Okay. Not a zero. This is not a zero. Okay. This is the capital letter O, meaning origin, and that we use by default to mean the point at the origin. Any other points we give other letters, A, B, C, D, and so on. Okay. So that green vector is effectively OA, right? It's the OA vector. So a point A has position vector OA, and that's it. That's effectively the really formal, the really key definition here. If you've got a point, that's how you get the position vector. If I had a point B, its position vector is OB, C, OC, and so on. Okay, and then finally, we want a very important property of position vectors, which is called the triangle property, the triangle law. Okay. Pay attention to the triangle law because you're going to be using it in some of these questions that you'll eventually do. Let's say I've got 2 points A and B, and they're on an axis. They're on a positive, not necessarily positive, they're just on an XY axis. And I want to consider the following vector, the vector that goes from A to B. Okay, so this is the AB vector. It doesn't start at the origin, so it's not a position vector. AB is not a position vector. All position vectors start with the O. But I can write it in terms of position vectors. And this is the triangle law. Okay. And this is how we do it. Consider the position vector of A. Okay, that's OA. Consider the position vector of B. That's OB. How can I write AB in terms of OA and OB? It's all about making a path that is the same. So one way of doing AB, of following that path, would be start at A and go to B. That's it. That's the AB vector. Another way of going from A to B would be, let's go from A, oops, I want to put O in here. Let's go from A to O to B, and I did the same path. So O to A to B is the same as A to B. Same path, same resultant vector. So let's write that down first. AB is equal to AO, A to O, plus O to B. And then think, really, that's just taking sort of the negative of the OA vector, right? In the first case. Opposite direction, isn't it? AO and OA are the same vector, just opposite direction. So I can write it like this. So finally, our triangle law, I'll just write it fully here, is the following. If you want the vector AB, you can sometimes, or you can always, but it's sometimes useful to rewrite it as OB minus OA. That is to say, the position vector of B minus the position vector of A. Okay, that's the triangle law. Really important. It's fundamental to the study of position vectors. So you want to really remember that. Position vector B minus position vector A gives me the vector AB. Cool, all right, let's look at some examples. Okay, 2 examples, then I'll give you questions. I appreciate it's a long video. It is because I've had to smash together 2 sub-chapters, but the plus side is this will give you more time to practice in later lessons, later weeks, okay, as long as you can cover the material. So let's look at this example first. We've got points A and B in the diagram. There they are. They have coordinates 3, 4 and 11, 12. I'm just going to write that on. That's 3, 4 and that's 11, 12. No, sorry, not 11, 12, 11, 2. Find in terms of I and j. We can do ij at the end. I just use column vectors for now. The position vector of A, the position vector of B, and the vector AB. Okay. So part A, what is the position vector of A? First, let's write that down mathematically. Position vector of A is this, OA. So that's going to be equal to, and this is really easy, the coordinate of A turned into a vector. So it's 3, 4. Or in other words, 3i plus 4j. Done. Position vector of B. This is the position vector of B, OB, origin to B. Same deal, 11, 2, 11i plus 2j. This is effectively going to use the triangle law. So then part C, the vector AB, and this is how we would write out the working properly. I want the vector AB. I'm going to use the triangle law, which tells me that this is the same as OB minus OA. And I have those two. OB is 11, 2. And OA is 3, 4, so I take that away. And I end up with 8 minus 2. And now I'm going to rewrite it as a ij notation vector. So that's 8i minus 2j. Okay? And if you look at it, it does make sense, right? It's 8 to the right and it's 2 down. And you look at the image and you can see, yes, indeed, from A, I go 8 squares to the right and I go 2 squares down. Okay. Obviously, at a more advanced level, you won't have these squares. You may not even have a picture. So you have to get used to doing it the mathematical way by using the triangle law. But hopefully that agrees with your sort of common sense. Right, final example. Let's take a look. So I've got 2 vectors. The first one's a position vector because it's starting at the origin. So OA is a position vector, and then AB is just some other vector. Find the position vector of B. Okay, so you can see at this point now, there's no image going on, there's no diagram. Just use the mathematical tools you have and your understanding of the notation. Okay, so let's not panic, let's just write things down formally. So first of all, OA is this. I prefer that to thinking about I's and J's. AB is this column vector, 3, 4. And we want the position vector of B, and that is mathematically asking us to find that, OB. Right? So then we remind ourselves, what was the triangle rule again? AB is equal to OB minus OA. We can rearrange that to make it say OB equals OA plus AB. Okay, all I did was add OA to both sides. So therefore, to answer that question, we're just going to do OA plus AB, which is this. So at the end of the day, all this question was asking you was, what is 5 plus 3? And what is minus 2 plus 4? And we get our answer, which is 8, 2. Then part B, find the exact value of the magnitude of OB, that's the magnitude, in simplified third form, in other words with square roots probably. So first we need to find what OB is before we can find the magnitude. Oh, that's what we've just done. So again, this is actually quite easy, just arithmetic, isn't it? The magnitude of OB is equal to the square root of the 8 squared plus the 2 squared, where the 8 and 2 were here, which is equal to 64 plus 4 square rooted, which is root 68. And then it said simplified third form, which implies that this can become simpler. So we need to think what square numbers are factors of 68. 4 is definitely one. So that would be 4 times 17. And 17 is prime. Okay, so it must be 4 then. So that's equal to the square root of 4 times the square root of 17. So we get 2 root 17. Okay, and that's our answer. Yes, it is 2 root 17. Okay, so see if you can try some questions yourself. So you've got here 3 questions. There is one more on the next slide, but you may not have time. So at the very least, see if you can try these 3. As always, just remember that you've got the blue references here that tell you where, in this case, it's the Blue Year 1 book, which chapter, which letter you can find the answer. Yeah, always at the back of the textbook. Okay, so give those a go. You can pause the video now. There is one more slide if you have time, but see if you can do these first. Okay, and if you're doing really well, see if you can do this. Hopefully it doesn't take too long. Give it a go, 3 marks.